Hey, so this is Module 5, Lecture 2, and we're going to be talking through multiple regression. So we talked about last time, right? Simple linear regression, so just using a straight line to predict outcome. And now we're going to kind of extend this out. You can't really graphically represent this that well, but right, remember we had an X and a Y, and we had some data points, and we basically fit a line like this. Now imagine that we have kind of a three-dimensional situation where you have multiple values here that end up forming a line in total. So how does, or partial relationships. So I might have, in the example we had before, I have weight here, W, and then I might have, okay, how does height affect weight? Okay, maybe as height increases, so does weight. And maybe as calories go down, weight also goes down. And maybe as, I don't know, greater than, 6 hours of sleep, maybe that also has an effect. So a decreasing effect. So this would be 6 hours, and you could see, okay, maybe weight goes down after that. So collectively, all these things together are going to get put together. You add them up, and that's how you get your predicted weight. So that's graphically the best I can do, sort of explaining how this works in that context. Statistically, all we're doing is we're assuming a statistical model that has multiple things. So in this example here, right, I would have weight equals, I'll call it, I'll just write it out like this. I'll call these H. So I've got beta 0 plus, I'll say beta H height plus beta C calorie plus beta S sleep. So that's what the statistical model looks like. It also has this same kind of error term on the end. And basically what we do is we get estimates for each of these things separately. So this is kind of like adjusting for all of them. So your interpretations here can be like, okay, as height increases, so does weight, after adjusting for these other potential factors that may influence weight. And there's more factors here that you might want to consider. I mean, like if you're diabetic, or if you have some kind of metabolic syndrome where you can't digest as well, those are all factors, or hereditary. I mean, even outside of, medical conditions, just some people tend to metabolize food not as well. So all those things could be factors in this regression. And that's kind of the idea. But partially, right, you can kind of represent these as the sum of a bunch of different graphs. Okay. So here are my lecture slides. So again, extending simple linear regression to multiple covariates. Simple linear regression is one covariate predicting one outcome. Multiple linear regression is more than one covariate predicting one outcome. So again, just as an example, we're still modeling this outcome variable y with P is a number, independent variables. So as an example, y could be weight as a function of x1, which is height, and x2, whether or not somebody lives in New Orleans. We have great food here. Maybe you intend to eat more, gain more weight. Observations for each individual look like this. We have each yi, each xi, and each x1i and each x2i. So like me, for an example, I am 5'11", so that would be my x1i. I do live in New Orleans, so I would have a 1 here, and my weight is 220, so my y would be 220. If I lived in Baton Rouge, my x2i would be a 0. Okay, so this is an indicator variable. So just like these indicator functions that we've been working along with, you can use these to categorize a 1 if somebody got a treatment or not. We've been doing that the whole time. So this is whether or not you're from New Orleans. Common types of y are continuous, binary. It could be, did they die or not? Time to event, y could be time to death, or count data. So we'll talk about in the next module, how do we deal with these later situations? So binary, time to event, and count data. But the general idea is the same. We're using multiple covariates in a linear, like in an added up fashion, multiplied by different coefficients. We use the data to estimate those coefficients. And then we can make conclusions about how each covariate itself affects the outcome after adjustment. It's going to be the same exact thing in the next module when we talk about logistic regression, which is another very, very common method that you'll see in statistical literature, in medicine, or whatever you're reading. You'll see that very, very commonly. So how's the factor here? So the goal is to model it like this: yi equals beta 0 plus, this is a sum of beta j times xji plus ei. So this looks pretty similar. The only difference here is instead of just a beta 1 and an x, this is replaced by the sum of multiple ones. And I just want to make sure everybody's on the same page. You know, this thing here, if p is 2, for example, so 2, this thing here, beta j, xij, this thing is just literally equal to beta 1, x1j, or this would say xji plus beta 2 times x2j. So all this is just shorthand. You're just adding up however many variables you're putting in here times their coefficients respectively. Okay, so this is just shorthand, and p is just the number of covariates here. And it assumes all observations are independent, which is the same as pretty much anything we talked about in this class. Assumes that the observations themselves are independent, which means my height, my weight, and me living in New Orleans does not affect your height, your weight, and you living in New Orleans. It doesn't affect that at all. I mean, that's usually pretty reasonable to assume. And we're going to assume that all the errors are all normal, these here. And then we use the data to estimate these coefficients. So again, we have this beta 0, this is our intercept. We have p of these beta j's, and then we're going to minimize the sum of the square errors, just like in simple linear regression. It's the exact same thing. It's just extended to multiple covariates now. So I can still test whether each coefficient is 0. So beta 1 equals 0. So as an example, okay, I can test whether conditional on whether or not you live in New Orleans, so adjusting for that, does increase height change your weight, or conditional on your height, does living in New Orleans change your weight? So I can test those things separately. And then also I can globally test, do any of these make a difference here? And so I can use this with an F test. This is like a NOVA. If I don't reject the null, it means that no covariates predict Y. So again, this is just kind of bringing you back to the last module. This is simple linear regression. You can see a line. It's a little bit harder to look at in kind of a multi-dimensional space or think about. But here we have individual errors are seen around the scatter of this line. So we have the same kind of thing going on. It's imagine like a cube, right? And you've got like this plane going through it. You're still going to get errors around it. It's kind of hard to visualize, so I'm not even going to try, but there is like this, from all these variables, there's a projected like line, and the data points are scattered around it. So again, as an example, we want to predict the weights of males as a function of height and whether or not somebody lives in New Orleans. So each individual are yi, x1i, x2i. And this is our regression model here. This is what we assume. yi is equal to beta 0 plus beta 1, x1i, plus beta 2, x2i, plus epsilon I. And let's just say we go out and we collect a bunch of data points, and we get this predicted model here. So we get beta 0 hat is 37.8, beta 1 hat, this is 202, and beta 2 hat, this is 0.38. So this is the New Orleans effect. If I want to predict the weight of an 83-inch male from New Orleans, I just multiply each thing together. I just plug in. So I plug in for x1, 83. I plug in a 1 for this x2 because they're from New Orleans. So their predicted pounds is 37.8 plus 202 times 83 plus 0.38 times 1. That's 205.94 pounds. Now I can test hypotheses about each of these things specifically. So again, right, if I test, H naught as an example, beta 2 equals 0 versus H1, beta 2 not equal 0, then what am I really testing here? I'm really testing here, after controlling for height, does being from New Orleans change your weight? That's basically what I'm testing here with this hypothesis. So it's an adjusted sort of thing. Here's how you read the output. So this looks the same. This is the LM function again. So just to kind of show you the LM here, I have LM. Let's say my variables are Y, X1, and X2, like their data points. I can do LM, Y, X1 plus X2. That's it. So I still have the formula. I just have to add up my variables on the other side. So here's my estimates. This is my beta 0 hat. This is my beta 1 hat. This is my beta 2 hat. And then these are the p-values here. So this is the p-value for testing beta 1 equals 0, which is testing, right? Does height change weight, conditional on whether or not you're from New Orleans. This second p-value, and it's significant, right? So we can say conditional on being from New Orleans, whether you're from New Orleans or not, increase height does increase your weight. This second p-value is testing whether being from New Orleans after adjusting for weight increases your, after adjusting for height increases your weight, and we do not reject this null. So that means conditional on your height being from New Orleans is statistically independent of your weight. That's a way to think about it. And this p-value down here, this is the one that tests, hey, we have any relationship between any of the factors we care about and the outcome? And since this value is significant, we reject this null. So again, height is a significant predictor of weight, but being from New Orleans is not. This R squared here, this is kind of like a squared correlation. So correlation rate is from -1 to 1. You square that value. It's more like a multiple kind of correlation. It's the variation in your weight explained by height and being from New Orleans. So bigger R squared means that your variables that you're including in your model better explain sort of how the data is varying. Okay, so let's think about how we could have done this ANOVA, right? So we did ANOVA using the AOV function. We totally could have done this using multiple linear regression. So let's look at the example where we wanted to know if heights are different, weights are different in Shreveport, Lafayette, Baton Rouge, and New Orleans. So I can create a couple different dummy variables. Here I've got a dummy variable x1i. This is equal to 1. It's an indicator if somebody's from New Orleans and 0 otherwise. I can do x2i equals 1. That's from somebody's from Baton Rouge and 0 otherwise. X3i equals 1 if somebody's from Lafayette and 0 otherwise. And then anybody from Shreveport in this, they'd have a 0 for each of these 3. So they have all these equal to 0. So this is the statistical model here that I assume. I have a beta 0, that's my intercept. I have a New Orleans versus Shreveport effect. I have a Baton Rouge versus Shreveport effect. And I have a Lafayette versus Shreveport effect. So if I get a significant p-value, then at least one group has a statistically different mean, which means I reject this null here. Now, I want to point something out. Why don't we have a variable for Shreveport? Basically, because, right, if you get a 0 for all of these, then we know you're from Shreveport. So if you take a categorical variable with multi-categories and you want to do ANOVA like this, you always have to create however many number of categories minus 1 indicator variables. So this is that linear regression output. This is testing beta 1 equals 0, beta 2 equals 0, beta 3 equals 0. These are all significant. So that means that the weights of people in New Orleans, Baton Rouge, and Lafayette are all significantly different from Shreveport. And you can see that since these values are positive, this indicates that people in New Orleans weigh more than those in Shreveport significantly. Same thing with people in Baton Rouge by about 25 pounds, and same thing in Lafayette. So this is actually what's being done in ANOVA. ANOVA, we talked about the last module, it's actually using multiple linear regression. Let's do another example, blood pressure differences. So I've got BPD, this is a blood pressure difference for patient I. BP1I, this is their initial blood pressure. And I'll say TI equals 1 if a patient received aspirin and 0 otherwise. So goal here is to model this, their difference in blood pressure. It's a function of an intercept plus their initial blood pressure times some coefficient plus their treatment indicator times some coefficient plus this error. And the benefit here is I can see if treatment changes blood pressure difference while adjusting for abnormally high or low blood pressure. Because, right, we noticed before, that in the last lecture, right, we noticed there was this kind of decreasing trend. So if you account for this trend, does the treatment change your blood pressure difference? So here, this is how I do the formula. First, I create my BP diff, just like we did before. And then I say M1 equals, so I'm just calling an object M1. You can use whatever you want, MR, X, however you want to do it. LM, I'm doing BP diff. It's got this formula. I say, hey, this is blood pressure 1 plus treatment. And here's my formula here. So I can see my formula. This is my p-value testing whether beta 1 equals to 0, which is testing, is there a relationship between initial blood pressure and blood pressure different? It's significant. I can go look at my coefficient estimate. This is my estimated beta 1 hat. It's negative, which means that increased initial blood pressure is associated with a decrease in blood pressure difference. And here's this treatment effect as well. This treatment effect is also significant. So here I can conclude that because this coefficient is negative, getting treated decreases your blood pressure change. So you have a bigger shift in the negative direction of your blood pressure. So your blood pressure changes more by being on treatment. And again, this p-value down at the bottom is just testing, is there any relationship at all? Cancer staging variables. I can also add cancer stage in this. So I can model this via dummy variables, right? So I've got cancer stage that can be stage 1, 2, 3, and 4. So I can create 3 dummy variables. Stage 2I, this is comparing stage 2 to stage 1. This is comparing stage 3 to stage 1. This is comparing stage 4 to stage 1. And this is my new statistical model here. So now I'm going to get extra coefficients. And I can actually do this here. I've got my formula, I've got blood pressure and treatment. And then I'm adding these indicators here. Now I have to wrap them in parentheses if you're going to do this in your function. And notice I still have the equals, and you have to put them in parentheses. These are those 4 indicators here. Now I get my results down here. So my results I can see as far as the initial blood pressure, it still significantly impacts your blood pressure difference. My treatment does impact blood pressure significantly. Patients that are on treatment tend to lose more blood pressure after adjusting for these other things. Whereas if I look at cancer specifically, all of these p-values are not small, which means that cancer stage doesn't affect your blood pressure difference in this data set. This data set suggests that, but instead aspirin does, and your initial blood pressure does. I can also do this a little easier using as.factor. So here I've got cancer stage here, and I just wrap an as.factor around it. Notice these are on 2 different lines because I've got this plus, otherwise you'll get a bug. And then here I give you, it creates the dummy variables for you. So here's stage 2, stage 3, stage 4, and I get the exact same results. Another way to do this is I can use the data step. So in LM, you can actually call a data set, and then I don't have to pass $ through everything. So you see here, right, I'm indexing data, blood pressure different, indexing data, blood pressure, all of that. If I say lowercase data equals whatever my data set's name, then I can just feed in the names of the variables themselves. I don't necessarily have to put data in front of it. It works the same. And you can do this as shorthand here. If I have a data set and I want to fit everything to my outcome, I can do this shorthand, which is y tilde dot. And the dot just means, hey, put everything in there. I can get confidence intervals for all my coefficients by using conf.int. So conf int of my M1, this is my summary object. You can see them here. And they work the same way, right? This blood pressure 1 difference is negative, both of them. It doesn't overlap with 0. So here we would reject the null that beta 1 is 0. One of the assumptions here is that the data is normally distributed. I can actually test this pretty easily by using the Shapiro-Wilks test. So the Shapiro-Wilks test assumes your data is normal. So if you reject the null, that means your data, your residuals are non-normal. All you have to do is use Shapiro.test. You're going to wrap the residuals in it. Whenever I do a regression like this M1 now becomes an object I can index with $. So if I want to index it, I can index with $, and I'll show you on the example kind of how you'd look at that. But if I index it with $, I'll see a drop-down menu where I can index a lot of things. I can index the residuals. So the null hypothesis here is that the residuals are normal. We don't reject normality, so we're good to go. Ways to fix normality. Usually if y is bigger than 0, so if it's positive strictly, sometimes modeling log y can help, or you can do some other transformation. Sometimes outliers themselves, abnormal Y values, may cause violations, and sometimes strange values of X may cause violations. Predictions, how do I get predictive values? Predictive values, I just plug in what I want for each one. So I can plug in a person's initial blood pressure. Did they get a treatment? Their cancer stage. I can plug them in and I can get a predicted blood pressure difference, and that's it. So for example, what is the predicted blood pressure difference for someone with stage 2 cancer, aspirin, and initial blood pressure of 170? So I just plug in their covariates, multiply them all up, add them together, and get the answer. So pet peeve for me, never call a multivariable regression multivariate regression. Multivariate means multiple outcomes. So that means more than one Y, not just weight. Maybe you're predicting weight and blood pressure. There has not been one time ever in my 10 years as a statistician where somebody who said multivariate regression was actually doing multivariate regression. Every time they've been doing multivariable regression. So don't say this. Again, in bold font, multivariable, not equal multivariate. And that's it. I just want to kind of show you just a quick example. I don't know, I've got X is our norm, Y is our norm, just feeding in some data. I don't know. For some reason, my thing's being buggy. So let's just go look at the homework and kind of talk through it, what I'm looking for. So if you go to the homework assignment, go to the assignment and open it. Yeah, my R is kind of freezing up. I'm running some stuff, so. So here is our thing. You want to load in this data in R. Let me just show you how to do it. I'm going to open a new R Studio. So you can load in the data set here by using this library mtcars function. So what you're going to want to do here, this is not a data set that you actually have to save. You're going to want to use this library equals mtcars like this. It's got to be, wrapped in the traditional parentheses sometimes when you come in here. Before you're going to do that, you're going to come to install packages. It's up at the top in your R Studio, and you're going to say mtcars. And it's going to install for you. And when I run this, why do I not have the data set? Let's see. I think actually now I just have to do, let's see, data. I just have to do this step here. So data mtcars, that will actually get you the data set involved. Now I can look at mtcars here. Here I can see what the data looks like. I can start indexing things, mtcars. This is my miles per gallon. I can go mtcars. This is my weight. I can do a linear regression, right? So I could say, M1 equals LM. I'll say mtcars. I don't want to give you all the answers. So I'll say mtcars. Let's go predict weight by mtcars of, I don't know, HP. I can run like this. I can summarize this object in one. Here I get my summary. Whatever HP is, increasing HP significantly increases weight. I can do multiples, right? I can add more variables here. So I can do weight plus mtcars disp. So here I can run like this. This is a multiple linear regression. Here I've got two factors. Now HP does not significantly affect weight, but displacement here does. And if you're worried about considering what these are, you can come here again, and this will tell you exactly what all these variables actually are. So here, this is HP is gross horsepower, weight is weight. So you can actually get that information there. And if I want to index like if I look at this, see if I type in M1, I can actually get to all of these things. So I can look at the residuals if I want. I can kind of sort through this however. So what you're going to do with this data set is plot DISP by miles per gallon. Does it look like there's a relationship? You're going to fit a linear regression to miles per gallon using DISP. Is there a significant association? And how does DISP affect miles per gallon? Draw the estimated regression line in your scatter plot. You're going to use AB line for this too. What's the estimated correlation between DISP and miles per gallon? Do you reject the null hypothesis that they're independent? You'll use core dot tests. And then the last question is, what is the estimated non-parametric association between DISP and miles per gallon? Do you reject the null hypothesis that they're independent? So this is a non-parametric test. What test was used? So it's pretty straightforward. I'm not having you do any multivariable linear regression, but I suggest just playing around with it for a second and just seeing what affects other things. So that's it for today.